Hello everyone, this is Mike Dowding with the SD Mines Physics Department, and we are continuing with Chapter 10 Material. In the last video, we covered the definitions for angular motion. We also saw how the mathematics pertaining to those definitions was exactly the same as what we had back in chapters 2 and 4. As such, we were able to rewrite the kinematic equations for angular systems, and we also had some expressions that allowed us to convert from angular motion to linear motion, depending on the radius of the circle that we were traveling around. So in continuing in this chapter, what we want to do next, the previous video basically took materials from chapters 2 through 4 and applied those to angular motion. And so that was almost exclusively kinematics. Chapter 3 did cover vectors and how we break vectors up into components, except when it comes to circular motion, we really only have two choices as to the direction that we travel, and that's either going to be in the positive angular direction, which is counterclockwise, or the negative angular direction. In other words, with angular motion, we do not have vector components that we have to break up. So continuing on, we now want to see how materials from chapters 5 and 6 relate to angular motion. And specifically, chapters 5 and 6 were about forces. And one of the first things that we learned in chapter 5 was that if we applied a force to a mass, it would accelerate at a rate of a, and the acceleration would be in the direction of that applied force. And from there, we could take information about the acceleration and apply it to things like kinematics, because our discussions on kinematics did not actually incorporate the mass of the object. And so chapters 5 and 6 were basically just an extension of the mathematics that described the motion of these objects. And so now what we need to do is we need to figure out where are the changes in angular velocity going to come from. Well, they're going to come from angular acceleration, but where is that angular acceleration going to come from? How do we take an object, like a wheel, and how do we get it moving? How do we get it spinning? And the obvious answer would be, well, apply a force to it. Well, how are you going to apply a force to that wheel? Are you going to apply it at the surface? Are you going to apply it somewhere between the surface and the center point? Are you going to apply the force at the center point? And then of all of those choices of where you're going to apply the force, what about orientation of the force? If I apply a force at the surface of the wheel, can I apply it perpendicular to the surface? Can I apply it tangent to the surface? Can I apply it at some angle in between the two? And so there's actually quite a bit of consideration that we have to give to where and how we apply those forces, because where we apply the force, how we apply the force, is really going to have an effect on how much rotation we see out of our object, and in turn that's going to determine how much angular acceleration we get. So what I'm going to do to help us visualize this concept is we're going to take a door, and over here is the hinge of the door. So obviously over here somewhere we would need a doorknob, and the door will open and close, swinging through some kind of angle or circular arc. And my first question is, why do we put the doorknob way on the other end of the door? Why don't we put it over here, right next to the hinge? And if you've ever tried opening a door from the wrong side, you'll know that applying a force very close to the pivot doesn't really work. You can still open the door, but it requires a tremendous amount of force to be applied at that location just to get the tiniest bit of rotation, whereas we can apply a very minimal amount of force on the other side of the door and actually get quite a bit of rotation. So this actually relates to a mechanical efficiency, but it also shows us that the placement of our force with respect to the pivot point becomes a critical relationship to how much rotation we're going to get. And what we're going to do is we're going to take all of these possible placements of force, and we're going to turn this into a vector. We're going to say that starting from the pivot or the hinge and then pointing outwards, this is going to be our radial vector. And the reason this makes so much sense is because as the door swings, the door is going to sweep out a path that is dependent on the width of the door or the radius of the door. Well, why do I want to turn the radius into a vector? Well, that's so I can see what direction the door is essentially facing at any given time. And I want to be able to relate that to the direction that my applied force is pointing. So to start off, we have this idea that where we place our force is going to make a big difference in how much rotation we get. But also there's going to be this relationship between the two vectors themselves. So to start off, obviously it's going to matter how much magnitude our force has. Obviously, the more force we apply, the more rotation we're going to get out of the system. But that rotation is also going to benefit from our being as far away from that pivot point as possible. And so the larger the value of R. So R is not only the placement of where our force vector will be applied, but it also has a vector direction associated with it. And then you'll remember we said that the orientation of the force. How do we apply that force? Well, we know that it's been applied at some given location, and let me draw a fresh door here. And we'll say that we're going to apply our force at a distance of r. So there's our force applied at a distance of r. But what if I applied the same force not perpendicular to the door, but parallel to the door? In other words, what if you grabbed hold of the doorknob and you started pulling in the direction of the door? Or what if you started pushing in the direction of the door? Would either of those result in the door beginning to swing? And the answer is no. And that's because I would actually need a force or a component of force that points perpendicular to the door or perpendicular to the radial vector to actually induce some rotation. So this is where we said, does it matter how we orient the force? And in fact it does. Any force that we apply to this door, maybe I apply a force in this direction. Any force that we apply will have some perpendicular and some parallel component. And those parallel components are not going to contribute to any of the rotation in the system. Only that perpendicular component will. So how do we match up the value of the radial placement of the force, the magnitude of the force, and the angle relationship between these two vectors? And when it comes to combining vectors, and that's what these are, we have a radial vector and a force vector. When it comes to combining vectors, we have two methods available to us. One is the dot product, which we're pretty familiar with at this point. And the dot product says you can take the magnitude of each vector and the cosine of the angle that exists between them. And that's one way that we can evaluate that vector product. Another way is the cross product. And this is something that we've not used yet in this course. But the evaluation of a cross product is not that different from the dot product. Instead of a cosine, we utilize a sine. So these are the two methods that are available to us, and we've already seen that it's force vectors that are running perpendicular to the radial vector that actually provide us with rotation. Well, if the force and the radial vector are perpendicular to each other, that means that their angle relationship is 90 degrees. So plugging 90 into both of these vector multiplication examples here, if we try using the dot product, cosine of 90 is 0, and so we don't get anything. Yet we already know from experience that pushing perpendicular into the door works very well to produce that rotation. Well, if we take the same angle of 90 degrees and we plug it into the cross product relationship, sine of 90 is 1, and we get a value of r times f. Now, does that mean that the angle relationship between f and r is always going to be 90 degrees? Well, no, because we said some of those forces could be pointing at angles that are neither perpendicular nor parallel, yet if we take the radial vector So I'm taking the radial vector of the door here, and I'm just going to move that force up, and I'll draw it kind of right at the tip of the door where it was being applied. In this case, we can see that there is an angle relationship between the radial vector and the force vector. And depending on, that's not a correct representation of measuring an angle relationship between these two vectors, but this is. We said that only the perpendicular component of force will actually contribute to the rotation. Well, as it turns out, that perpendicular component uses the sine relationship of the angle, and so that's where we get the sine evaluation of the cross product. So we now have a means of finding out how much rotation will be produced by applying a force at a given radial position. And as long as we know what the angle relationship is between those two vectors, we can evaluate how much rotation we're going to get. And we have a term for this, which we call torque. So torque is the measure of how much rotation, or the rate at which this force is going to provide rotation for our object. And as you can see, I have written torque as a vector, and that's because with the cross product, the true name for this should be the vector cross product. Anytime you take the cross product of two vectors, the result is another vector. The dot product, also known as the scalar dot product, always results in a scalar. So in that case, we take two vectors and we turn it into a scalar. With the cross product, we're turning our two vectors into a new vector. So the torque is a vector, and the torque is going to be like our force analogy to angular systems. And what I mean by that is back in chapters 2 and 4, we had all of our linear expressions for displacement, velocity, acceleration, and then we had our angular equivalents, where we could just take the terms from chapters 2 and chapter 4, and we could just replace all of those terms with the new angular equivalents. The only one that didn't have an angular equivalent was time. But now, instead of having just a force, we need torque. In other words, it's not enough to know just how much force you're applying to some object that you want to rotate, but you need to know where it's being applied and how it's being applied. And that's what our cross product does. It tells us what the angle relationship is between those two vectors. Well, let's see if we can do this this term for term rewrite that we've been playing around with. We had a lot of success with taking the 5 kinematic equations and rewriting them in terms of the angular equivalents. So let's take Newton's second law, which says that F equals ma. And let's try rewriting it using the angular equivalence that we've come up with. Now, we already know what our angular equivalent for acceleration is going to be. It's going to be angular acceleration. And we said that instead of force, now we're going to use torque. Oops. Getting too close to the bottom of the screen there. Now, both torque and angular acceleration are vectors. And remember, when it comes to angular motion, you only have the two choices when it comes to direction. But then we have to bring down the mass equivalent of our system. And most people would just say, well, mass is mass, so plug that in there. Except that's not going to work. And one way that we can show that that's not going to work is by looking at the units. For angular acceleration, we have units of radians per second squared. For torque, let's come back up here and look at what we're using for torque. We're using meters for the units of the radial vector, and we have newtons for force. And so the units for torque are Newton meters. And if I try to set that equal to the other side, well, mass only has units of kilograms. And a Newton meter is technically a joule. In other words, torque is a means in which we can do work or transfer energy. And this is why if you've ever known anyone that works on cars, torque is usually a term that comes up a lot because the better the torque, the better the speed of the vehicle. And that's because when you have more torque, you are transferring energy from the engine and the drive axle to the wheels at a higher rate, which means that the vehicle can go faster. It can accelerate faster. So torque is really a means of transferring energy, and let's see, if we really needed to, we could deconstruct the Newton into a kilogram meter per second squared. We've got an extra meter there, but I don't have any meters over on the right hand side. All I have are radians. And so what that tells us is that either we did something really wrong with the previous math, or it's not enough just to have the mass of the object in the expression. And so what I would like you to do at this point is consider some objects that all have the same mass but different geometries. And the one thing that we're going to bring in from Chapter 9 to help us out is the idea of center of mass. Given the distribution of mass throughout the volume or the geometry of these objects, we'll go ahead and assume that each of these objects has uniform density. And so that means I could do some half cuts. Oops, that wasn't a very good half cut there. We could do some half cuts through the system here and find the center of mass for each of those objects without too much hassle. And these are going to be the points where each of these masses actually rotate. These are going to be the pivot points for these objects. And so each of these objects has the same amount of mass. Well, as the wheel turns, we have particles of mass located all throughout the wheel, and these particles have to go around in a circle as the wheel spins. For the triangle, we have masses that are distributed out, and these have to travel around in a circle as the triangle spins. And then for this large rectangle here, you've got a few layers of mass that go up and down, but then there's a lot of particles that extend outwards at a pretty far distance, which means that they have to travel through a much greater displacement than any of the particles inside of that wheel, or even that triangle. And so the question becomes, even though all three of these objects have the same mass, are they all going to be as easy to rotate? And if you've ever, had a meter stick or something, and you spin it around its center point, it takes a bit of effort to spin that stick around in a circle, because every one of these points on the ends has a very large displacement that it has to get around. Whereas all the points on the rim of that wheel, they do have to get around in a circle, but it's not nearly as large as the outermost path on that meter stick. Let's try another analogy. Maybe you have a pen or a pencil, and you take that pen or pencil and you start spinning it around in your fingers. Well, the endpoints of that pen or pencil are going to have a pretty good distance that they have to travel around. Yet, if you took that same pen or pencil and just rotated it around, you just kind of roll it back and forth in your fingers, you're taking the same mass of that pen and you're still rotating it around in a circle, but the path of the circle that you're taking now is equivalent to the radius of that pen, which is probably not more than a half a centimeter at most, whereas the radius of the pen over here, as you're tumbling it end over end, is probably something closer to 6 or 7 centimeters. And in which case can you spin the pen faster? And the answer is going to be right here. It's going to be a lot easier to move the pen and rotate the pen along its central axes than it is to try and get it to tumble end over end. And the reason for that is because the majority of the mass that you are trying to rotate is very, very close to the pivot point of the pen. Whereas in the other situation, you have more and more mass located at a further radial position from the pivot point, and it's more difficult to move that mass through that greater displacement than it is to try and move the mass through a smaller displacement. And so it turns out that the mass is not the only story. We also have to consider how the mass is distributed. So how is the mass distributed around the pivot point? And long story short, the more mass that you can keep closer to the pivot point, the easier it's going to be to move or rotate that body. And there is a way for us to take that into account mathematically. What we need to do is we basically need to add up all of the individual particles of mass with respect to their individual locations. And if that sounds familiar, it kind of is, because that's what we did back in Chapter 9. We were finding the center of mass for the object. But center of mass, that's only the first step. The center of mass really just tells us where the pivot point for each of these objects is going to be. It doesn't entirely tell us how that mass has been distributed through the system. So what we're going to do, since we're going to add up the influence of all of these individual pieces of mass, we're going to start with a summation, because we're adding things up. And let's take something like a wheel, just a very basic shape of radius r. And we'll also assume uniform density. So we have the same amount of mass per unit volume everywhere inside of this wheel. And we're going to take a very small sample of this wheel. We're going to take this tiny little piece right here, and we'll call it dm. So this is an infinitesimal amount of the mass. In terms of the summation, we would need to take each individual mass times its individual location, and we want to make sure that we're not including any minus signs anywhere. And so what we're going to do is we're going to square the radial value just to make sure that we end up getting a positive outcome. But this is also going to help with the units later on. And this summation is going to produce a new term which we call inertia. The full name is rotational inertia. And inertia is going to be the mass equivalent for our rotating systems. Now the summation works well if we have a particle system, but most of our objects are going to be three-dimensional. They're going to have millions, if not billions, of different particles inside of them. So what we want to do is we want to upgrade this summation using some calculus. And summations are really just the foundation of the integration process. What we're going to do is we're going to take those individual masses and we're going to integrate about the dimensions of our mass, or the dimensions of our object. And this is where the idea of inertia can get kind of tricky, is how do we incorporate the limits for all the different kinds of shapes that are out there. What is the radius of a circle versus the radius of a sphere versus the radius of a shell versus the radius of a solid cylinder versus a hollow cylinder. And so the geometry can really take a whole lot of different paths depending on what kind of shape you're using. But it's at this point we would probably be better benefited to look up whatever shape we need in a table of inertia values. And so in our book, in the Read Study Practice section, there is a table of 9 common shapes that we're going to use, and I'll just go ahead and draw these out here. I'm not going to be able to do as good of a job as what the book does. But we start off with a very thin hoop, which is rotating about its central axis of radius r. And everything in this table is going to have the same mass of m. And the rotational inertia of our hoop ends up being mr squared. Next, we have a cylindrical hoop, and the cylinder has a given thickness. There is an inner radius of r1, there is an outer radius of r2, and a length of L. So in comparison to the thin hoop, the hoop doesn't really have a thickness between the inner and the outer radius, and it doesn't really have a length. Yet for this thick-walled cylinder, the math starts to get a bit complex pretty quick. And if we take the rotation of this cylinder through the central axes, it turns out the length of the cylinder actually does not contribute. The length of the cylinder is not going to contribute until we try to rotate that cylinder about something other than the central axes. And so a third example here would be for a solid cylinder. And you can probably figure out what that would be from the previous case. So here we'll just have a radius of r, and we're rotating about the central axes. Again, we have a length of L. Well, let's say that the radius of the solid cylinder is the same as radius 2. And radius 1 was 0 because, well, it's a solid cylinder now. We don't need the inner cylinder. The inertia for the solid cylinder will end up being 1/2 the mass times the radius squared. Well, let's try something a little different. Let's take that same cylinder of radius r and length L, and let's try rotating it about this axis. Wrong color. Let's try rotating it about this axis. So over here, we were basically allowing the cylinder to roll, but now we're forcing the cylinder to rotate about its length. And what that means is that you're going to have a considerable amount of the cylinder's mass at a greater distance from the focal point as what you did for anything in the previous case. And so this particular inertia, in addition to having a greater mass distribution throughout, is also going to have a more complex mathematical expression. But if you compare the inertia here to the values that you're getting here, depending on the actual length of that cylinder, this inertia is going to be quite a bit higher than what this inertia was. It's going to be more difficult to rotate this cylinder than it is to rotate that cylinder. And this is something that you can try next time you go out camping. If you're roasting hot dogs or something, you can try skewering your hot dog through the central axes of the hot dog, or you can try skewering the hot dog right through the middle, and then spin them both really fast and see which one breaks first. And I can guarantee you it'll be this one. Alright, well, what else is there? We took the solid cylinder and we rotated that about 2 different axes. Let's try the hoop. Let's go back to that hoop. And instead of rotating the hoop through the central axes, let's try rotating it right through the top. Again, same mass. All these objects have the same mass. It's just a difference of how everything has been distributed in terms of the geometry. And in this case, we're going to end up with half the rotational inertia as what we did in the first case. Next, we'll try a sphere. And you might think, well, what's a sphere except a three-dimensional circle? So we have a sphere of radius r, and there's really not a whole lot of different ways that we can spin this sphere. The only thing that I'm going to insist upon is that we rotate through the center of mass of the sphere. And because of the geometry of the sphere, you can really put that axis of rotation anywhere you want. The symmetry of the system is going to provide the same rotational inertia regardless of how we set this up. So we've got a sphere that's spinning on its central axes. So this hoop was spinning on its central axes. This one was spinning like this. This was spinning like this. And the rotational inertia of our sphere is 2/3 mr squared. Now, if you're wondering where I'm getting all of these expressions from, remember, these are all going to come from this method. And the setup of the calculus and the geometry, especially in 3D, is not something that we're prepared for at this moment. But after you get through Calc 3, then you should be able to take an idea like this and reproduce all of these expressions. But for now, we're good with just having the expressions and actually being able to use them. Now, the next case that we're going to see is, well, another sphere. And like I said, how many different ways can you skewer a sphere? But this time, we're going to distinguish between this sphere being a solid and this sphere being a shell. So we have a very thin shell. All the mass of this sphere is now contained within a thin shell at radius r, whereas this sphere had all of its mass distributed uniformly from the center point out to r. And just as a quick thought experiment, which of the two do you think will rotate easier? Will it be the solid or will it be the shell? And remember what we said before, the closer the mass is to the point of rotation, the easier it's going to be to rotate. The more mass we have further away from the pivot point, the harder it's going to be to rotate. And so the answer is the solid will rotate easier. And that's because the shell has the majority of its mass further away from the pivot point. The inertia that we get in this case is, oops, I had an error. Make sure you go back and change this. This should have been 2/5, and the shell is 2/3. So 2/5 is less than 2/3, and the smaller the inertia, the better. The smaller the inertia, the more rotation we're going to get. And I'm actually going to skip the well, I can put it in here. The last example that our book has for inertia is a rectangular slab. So we have a thin rectangular slab of dimensions A and B. And if we rotate through the center, or the center of mass of that slab, the inertia comes out to be 1/12 of the sum of the square of the dimensions times the mass. So why do all these inertias matter? As we said, it all has to do with how the mass is distributed throughout the object. And now we're going to take our torque expression, which was our force equivalent for rotation, and now we know what the mass equivalent for a rotational system is. It is inertia. So with torque, it's not enough to know just what force is applied. We need to know where the force is applied. We need to know how the force is applied. With mass, it's not enough to know the mass of the object. We need to know the geometry of the object and how that mass has been distributed through the object. After that, then we get an angular acceleration, which we can apply to rotational kinematics. So it probably wouldn't be fair unless I gave a quick example. Let's take a solid cylinder. So this could very well be the tire on your car. We'll take a solid cylinder of radius r and mass m. We'll let the radius be 1/2 meter. The mass can be 10 kilograms. And I am going to apply a force to the surface of this wheel perpendicular to the radial direction, or tangent to the surface of the wheel. And what I want to know is what will be the angular acceleration of this wheel. So first and foremost, we're going to take our new and improved version of Newton's second law. This is actually called Newton's second law of rotation. Now, that does not imply that there is a first or third law of rotation. This is just Newton's second law rewritten for a rotating system. But torque equals inertia times acceleration. I can look up the inertia of a rotating cylinder. I'm fully expecting that this cylinder will begin to rotate about its central axis. So I'll look up in the table what inertia best fits that situation, and it's going to be this one right here. If you ever run into another shape that is not on this list, I can pretty much guarantee you anything in the homework or a test will be on this collection right here. But if you do end up with some other shape, you can probably find it online or in a book of inertia values somewhere. But we have an inertia that is equal to 1/2 the mass times the radius squared. So let's just go ahead and get a number for that right now. We have 1/2 the mass radius squared. The radius squared is going to be 0.25 times 10 is 2.5, and 1/2 is going to bring that to 0.125. Double check my work here on my calculator. Oops, got my decimal in the wrong spot. It should be 1.25. Well, so what are the units of inertia? If you noticed, with all of our examples here, the units in every case are the same. In every case, we have a mass term and a squared radial term. And so the units are going to be kilogram meters squared. And that's actually the appropriate value that was needed to make all of our units work out properly before. So 1.25 kilogram meters squared is the inertia value. To get the angular acceleration, I will need to find the torque and divide by that inertia value. So how do we get the torque? Well, that was the first part of today's discussion. We can find the torque by taking the cross product of our radial vector and our force vector. We know how much force is going to be applied, even though I didn't tell you. I'm going to tell you now. We will apply 100 newtons worth of force to this cylinder. And remember, I said that this force was going to be applied tangent to the rim of the cylinder or perpendicular to the radial direction. And it may not look like it because I've drawn the radius like this, and I've got the force like this. Well, keep in mind that we placed the force right here. The force is influencing our cylinder right there. I need to know how that force is oriented with respect to the radial direction, or the radial vector. Great thing about the radial vector is that it always points radially out. So I'll start at the center and I'll draw a line that goes right through that placement of the force. And there's the direction of the radial vector. The magnitude of the radial vector is just the radius value, 0.5. And as we can see here, there is a 90-degree relationship between F and R. So in evaluating the torque, we have magnitude of radius, magnitude of force, sine of the angle between the vectors. We have 0.5. We said the force was 100. Angle between the vectors is 90. Sine of 90 is 1. And so we have a torque of 50 Newton meters. And we're home free. We have 50 Newton meters for the torque. We have 1.25 kilogram meters squared for the inertia. And let's see here, we can get rid of a couple of those meter terms. We can also take the newtons as kilogram meters per second squared, and we can cancel out kilograms and kilograms. And let's see here, do I have one too many meters? Yep, I do. But that's actually okay. I lost all the meters there, and that's okay. That's actually a good sign. Because now what's left, we have 50 divided by 1.25, which is 40. And the only thing that survived out of the units was the 1 over s squared. And we're trying to solve for an angular acceleration. Well, from the previous video, we know angular acceleration should be in units of radians per second squared. Well, where are the radians? And if you watched the previous video, I told you that whenever we convert back and forth from linear values to angular values, we will often have to either add or remove the radians when appropriate. And so I always tell my students, if you're not using the radians, put them in your back pocket until you need them. Well, now is a time where we need them, so we're going to incorporate those radians back into the value. So this 10 kilogram cylinder of half a meter is rotating with an angular acceleration of 40 radians per second squared, which is actually pretty fast. If we assume that this cylinder started from rest, and it's accelerating at a rate of 40 radians per second squared, how fast is it going at the end of 5 seconds? So now we're right back to an angular kinematic equation. Not only that, how much of an angular displacement have we gone through? So first things first, we'll go with the final angular velocity. We'll grab the appropriate kinematic equation for that, which is this one. We plug in the values of our angular acceleration and our time. And so we're getting a final angular velocity of 200 radians per second. Next, we'll go and solve for the angular displacement. And for that, we would prefer to use the equation that does not use the final angular velocity. And so this is the equation that does not use the final angular velocity. And we'll plug in our values for this. 0 for the initial velocity times 5 is still 0, plus half of 45 squared. And this is coming out to be 500 radians. And one more step. We have this cylinder which is rolling down the street. Where'd my cylinder go? Here it is. So we have this cylinder which is rolling down the street. It's effectively rolling down the street here. So I would like to know physically how fast is that thing going, and what is the displacement through which that cylinder has rolled down the street. And this might sound like a difficult thing to answer, except that we've already done that in the previous video. We know that we can take things like angular displacement, angular velocity, angular acceleration, and we can convert those back to the linear equivalents. We know that our cylinder of half a meter is going to roll 500 radians angular displacement. As such, that's going to work out to be 200 meters in linear displacement. Likewise, we know that we have a final angular velocity of 200 radians per second on a half meter wheel, which will result in a linear velocity of 125 meters per second. So pretty fast, but that's what happens when I make up the numbers as I go here. But the way that we can kind of visualize this is when you have your cylinder rolling down the road. Take that cylinder, which has a circumference of 2 pi r, and unravel it. So every 2 pi r, or every full rotation of that wheel, will allow you to travel a physical displacement of 2 pi r on the ground. And so knowing what the full angular displacement is, we can relate that back to the number of turns, or the arc length, which is unraveled on the ground as we roll. Likewise, the rate at which we roll can be related to the rate at which we travel along the ground, giving us that linear velocity. And so now the final step would be, well, how fast are we accelerating as we travel down the road? We can get that from the tangent acceleration of this wheel. The acceleration that we got was 40.5, and so we have 20 meters per second squared is the tangent acceleration, which means that's how fast we will be accelerating as we move down the road. So a very, very powerful use of the mathematics, because now we can take the idea of applying something like torque, or a transfer of energy from the engine, transfer that energy through a drive shaft to one of the wheels on your vehicle, which has a certain radius. And depending on how fast that wheel is rotating, depending on how fast the wheel goes through an angular acceleration, then we can come up with all of these other values, which seem to be more important to us, like how far can we get, how fast can we get there. So all of those things that kind of get us in trouble if we have a lead foot in traveling too fast in our cars, at least. But also very, very, very useful in any kind of mechanical system involving gears or anything that happens to be rotating, which, let's face it, is a lot of stuff. So I'm going to quit the video there because it's actually raining and thundering outside, and I would like to save my progress just in case the power goes out. So we should have about 2 more videos after this, and I'll see you at the next one.